launching in. This is just the quick overview. So again, I don't know, maybe everybody was there. So OpenCV is an open source free computer vision library, BSD license. So it's non-infectious. You can have a for money library and incorporate the whole or parts of OpenCV or code. And it runs on all the platforms at the bottom. And languages, C++, Python, C#, there's a C interface, and Java. And I'd gone over this in the other talk, but it covers a huge number of areas. It's one of the reasons we find it useful in robotics, because it sort of covers everything to some extent. And same slide from the other lecture. This is more or less just the architecture of OpenCV. You have the languages and its specializations for CUDA, SSE, the optimizations. Then there's third-party libraries that you can use or interoperate with OpenCV. And on the right, your right, we're breaking OpenCV up into these smaller and smaller modules that are hopefully independent. And we have these target architectures and OSs. So again, another slide of going through OpenCV. Where is it used? All over the place. More than 6 million downloads. Getting now 160,000 downloads a month. And this is the same old slide, so that's just showing it that we've passed 6 million downloads and 160,000 this month. I don't know, how many more vision people are there out there in the world. This seems to account for nearly all of them. But and as I said in the other talk, this is now a foundation, and I am looking for corporate support in varying chunks, and as low as 5K and 10K for development sprints, and 1K you can start getting guaranteed support or return on bugs and questions within a week, on up to 30K is 24-hour support turnaround. Okay, so now that was OpenCV. So robotics, this is just going through, I don't know, are anyone out there working on robotics or robotic applications? 1, 2. So more of an embedded crowd. But of course, robotics has a lot of embedded vision. The more the merrier for us. So, robotics 1.0, what I'm calling it is blind, dumb, repetitive, but accurate and limited. So, the paradigm robotic application has been welding. And so, the whole structure of the robotic industry is kind of around this thing. These are blind and dumb, so the whole line of cars, 100 yards or 100 meters of them, is aligned with sub-millimeter accuracy, so these welding robots can weld. And that takes a lot of planning and organization and orchestration. These robots are choreographed by waypoints that you have a little pendant and you program in. It's really like 1980s technology. They even, basically you have this ladder logic you program in, and it's the throwback to resistor ladders, right? But now it's digitized. So, I mean, it's the industry's been stagnant in a way for a long time. The arms themselves are amazing. We've smashed these things into walls, and the end effector gets crumpled, but the arm is like still millimeter accurate, right? It's not even bothered. So, some of the engineering is just great on them. And others is horrible. Their controls, their electronics, their software is terrible. So that's robotics 1.0, but it's been a successful industry, right? And it tends to go to places where it's high margin, long shelf life, and rigid, and that's car. Right, and iPhones could be assembled completely robotically, but it takes so long to fixture and organize this that you're on to the next phone by the time you get it solved. It's about, I don't know, can be 14 months to set up the robot line to get the whole thing working. Anyhow, this is this is how they do it, blind and dumb. They fixture it. And there's things that hold the objects, and then you have to, have this clever mechanical engineers figure out how these parts work. And you also have people, this is from a assembly line in Procter & Gamble, who have to straighten the stuff out so that it feeds in right, and that's their job. They sit there for 6-hour shifts straightening out little lines. So it's because the robots are very inflexible, they need things perfectly fixtured. So now we're on to robotics 2.0. And that's where we are. And basically 2.0 means we're moving towards greater and greater levels of variance. So right now we don't believe in the home market because it's just too variable, but we believe that the next stages in manufacturing logistics can be expanded. So our company is adding, perception, control, and planning, a lot of planning. So industrial perception is not at all a vision company. It's very much, perhaps even more weighted towards planning. The motion planning, the movements, the organization, none of that's in robotics right now because they had carefully scripted movements, but our arms never move the same path twice. In 10 years of running, the robots will never move the exact same way twice. So, because they're being driven adaptively. And so that breaks a lot of the paradigms. We're having to get rid of the controllers and wire in directly to the motors and all kinds of stuff to get the performance we need. So again, we're moving towards being able to handle more and more variance. The stuff that we're moving isn't exactly placed or exactly aligned. It just shows up, a perception handles that. And then you see in this movement, more and more variance. So you get to a home, everybody's home is very personalized, and people and pets and babies are fragile. And so, we're starting up with logistics and manufacturing, where you have more limited domains, but we still want to make them more flexible, okay? So the perception needs are recognition and pose, and so it's not enough to know what the object is. We have to know where it is in 3D so that the robot can manipulate it. That's the whole point, right? So one way, if you have textured objects, is basically you can learn a constellation of features on an object in 3D, and then when you find some of those features, you suppose you solve for a rotation and translation matrix, and you carry all the features over. If they match up, then pretty surely you've got your object and you've got your pose. And so you use a routine called ransack to do this random sample consensus of taking a subset and then fitting the whole, and to throw out, to maximize inliers, throw out outliers, and so there's a whole technique based on that of using key points and determining poses of objects. And this was developed at CMU called MOPED. At Willow Garage, we developed something called TOD, Texture Object Detection. And we're not really using this right now, but we might. And so this was in ROS. And again, so we're, here you can see this Odwalla bottle. We've got key points, and we're matching it. So this was learned as a model, and then it's matching to the scene. So we know relative to the model what the rotation and translation is, so a robot could grab it. And it's also giving us a confirm that that's the object. So this is just on one side. It's just showing the key points. These aren't actually quite synchronized. They are a little bit. But basically, these object models have been learned with their feature points. And this is just showing that, it's able to match them. So overlay the model on top of them. Of course, this was the first pass we got working, and I haven't worked on it since. So it was a little bit slow, but I mean, this is handling many objects. I think we had like 20 going. 20 objects loaded. There's only 5 or 6 here. So that was decent for what it was. But it's getting the pose, and it's fairly robust to occlusion and all kinds of stuff. So it's a decent technique when you have a lot of texture on objects, such as consumer grocery items. Of course, in industrial apps, we often we're handling boxes that have no features or only evil features on them. I started out in robotics working on Stanley, this robot that won the DARPA Grand Challenge. So DARPA put up $2 million for a race across the desert that was supposed to build up autonomous supply lines for DARPA. Interestingly, that never happened because we pulled out of Iraq and the military lost interest. But this technology went first into Street View. So Street View was built out of Stanley's engine, and then into the Google car. And it's been a big area ever since. It's kind of interesting. All these people have gone on to other places. Hendricks had started 2 companies now, both of which were bought into Google. So he's making a living of just selling to Google. So this was Stanley, the car that won the DARPA Grand Challenge that I worked on. It had the vision system, and it had all kinds of sensors, 5 lasers pointed at different angles to integrate the ground. Now we have LiDAR that's spinning Velodyne, but that wasn't invented yet. Has GPS, and let me go back. The brains were in the back, and there's one little camera up here, and it had a GPS and GPS compass, and wheel odometry and a bunch of other systems. And so, the way inside its brain, what would happen is the 3D world would create a world model, and it would ship a map to both the vision. And so it would serve as a seed for the vision system. And then these maps would feed into a planner, which was actually a physics simulator that ran the car through its trajectories. In the morning, if you heard Peter Abill's talk, it was the same thing. We'd run the trajectories out for a couple seconds, and then the car would take a 1/10 of a second step, and then it would recompute all these trajectories, so it would take these optimal paths. And there were strategies on how to maintain speed and the whole thing. But this was the brain, but it's very much the same in what we're doing industrial. We have perception, but planning is at the center of it. So motion has to be planned, and it's actually any of these areas that you get into turn out to be extremely hard when you get into them. So how we move is a miracle. How we see is a miracle. It's very difficult and ill-constrained problem. We have a lot of joints. How you decide to organize the joints, they have redundancy, and et cetera. So that was Stanley's brain in its little car world. Basically, what the vision system would do there is the laser would give it a seed and say, I like this, find me more of it. And the laser couldn't see out far enough, actually, to drive full speed. And the car needed to go full speed. Races are won where on the shortest parts, where you can go fastest, you must go fast. And so, basically, we built this Gaussian model of to segment the road, and then the car could go faster than it could stop in the laser. And whenever it got into problems, it would slow down into laser speed. But this thing was running. That's it's building out the plan. So you see bad trajectories and good trajectories, and it's taking the middle one, and it's always building out the system by fusing this far-range vision with the short-range laser. And so this was the race. This car worked. The vision system ran 7 hours. And never failed, right? So it was a fair accomplishment. We kept the vision system very simple. It was a Gaussian model in the end. We had better models, but Sebastian Thrun didn't want the better models because they were more complex. And he thought, we don't really know what the conditions are. We want simple models that we can understand failure conditions on. So this was the start of the DARPA Grand Challenge. CMU started first, finished second. They had that big scanning laser up there. We just had fixed lasers. It was getting radio interference, so it lost GPS there. But So, the result, this was dropped by the military, but it spurred many civilian applications, and of which, Street View and the Google car are two. There's others. So I went to Willow, and then we decided to gather a small internal group and pursue industrial applications. We thought we would be entering, you can't really see it. The company's motto is we're providing robots with the skills they'll need to succeed in the economy of tomorrow. And we thought we'd enter manufacturing, but it turns out logistics is even more befrit of robots, and so a lot of what we do is just moving boxes, and it turns out there's a lot of boxes in the world. So these are our areas, our navigation. We got carts that go into trucks and unload them, calibration, pick and place, and on and on. I'll speed up. But so we have all these full navigation technologies. We understand surfaces and can track motion, because the robots have to find where they're going, find where the boxes are, and pick them up. But I'll skip on. So navigation's one technology. We have a very cheap system built out of Connects that can, understand surfaces to allow robots to roll over them. Calibration, is this going to go? So robots use tools all the time, and the tools get damaged, and you have to know and be able to measure it. And this here is something we were asked to do with welding tips. And so that little wire that comes out can get munged or broken. And basically, this is an expensive system, measures this by laser. We just took a webcam and put it on telephoto lens, and then put a diffuser in the back, and we can measure this sub-millimeter. And then I built software for just sort of reconstructing the 3D of this tool, just because you can move it around, so you really don't need much else. And so that's metrology, so measurement, accurate measurement. Moving on. We do a lot of model building. In fact, that's how we train our systems. When we get something, turn it around, get a 3D model, and we use that to train the classifier. So we don't train by hand, we actually just capture a model, or we could get a CAD model, and that internally trains the classifier. I think I'll skip this one. So we can put something on a calibration pattern. We can actually just use newspaper, turn it around, and you get a 3D model, and this is just showing that. But I'm going to move on for some other stuff. Here should be 3 videos starting. The first one up left is there's an object being learned. This is our learning system. Or it can be, here's 3D captured model, but here it's just being learned by the camera. There it's being, we've captured a model. And below it's being used, so it takes a while to see, but the model is being overlaid. So there's a vise there that's in gray, but that's a projection of the model over it. You see after a while it picks it up and its thumb disappears because it's being projected. So this means we have that recognized. You'll see the coordinate system below that. And we know it's posed. If it wasn't, entirely synced up, and this isn't sped up, it's real time. If it was a mismatch, you would see the shearing of this. And as this video goes on, we get more and more models. Again, this is, upper right is it being used. Here I just trained that, and that's all in real time. I spun it around, and now it's being used to recognize parts. Below is much more careful training, and we have more accurate models. This is what we use, and we use it for everything we do. If it's simple boxes or complex things, this is one of our core algorithms. Simple geometric objects can just be, mathematically. You don't even have to scan them. You can define them mathematically and train that way. So, moving on. Here's another thing we do. Our sensors, this cheap Connects aren't good enough to see sub-millimeter, which we need to see when we're finding like cracks between boxes. And so if you see below, here's a smooth surface. We're actually doing this, they call Connect Fusion, but but we're integrating onto surfaces to get hyper resolution. And this is just one of the tricks we use. We're designing better sensors so that we don't have to go through so many hoops, but right now that's what we're stuck with. This is the truck unloader. I don't know how long I'll let this go. So this is a bunch of videos of it. This is one product that's out there. We're redesigning it from scratch now that we know what to do. But this is actually being marketed by a company that's a partner of ours. And now we're just building it by itself. So this bottom left is the robot eye view. And top left is the robot navigating to the back of a truck. On the top right is it's loading, so we do loading and unloading. And the bottom right is this navigation. So eventually this thing will go to the back of the truck. I might be running short of time. And it'll grab boxes and load them onto a conveyor belt that's dragging, it drags behind it. It's a extensible conveyor belt. But got other videos. Okay, so this is another technology. This is automatic pick and place. That is for, like, bins come full of stuff for the robot to pick it up and put it in other boxes. So it's hard to see in this blurry video, but we have this on our website. It's got a model that it's looking for, and it scans the whole scene to make sure there's not more than one. If there was more, and then it comes down oriented to the surface. So it's hard to see, but if you can look and squint, it's putting a mesh over the object, so it's really got it locked in 3D. Again, this is one of our core algorithms that's being used to drive this robot. The robot also has all this planning. It's not being demonstrated here, but it orients itself to go in, and it's got a cable on it that it never breaks, because it'd be easy to twist that thing around, but it's making sure that it doesn't. So it's doing a lot of things that you don't expect, but it can also plan over and under obstacles in real time, which is revolutionary to roboticists, but simple to people in academia. This thing is robots throwing boxes. It was actually done as a party, throwing party favors at a billionaire's birthday party. But we liked it, so we kept it. Whenever people come in, they get this demo and they have to catch boxes. We tell them one's full of nickels. So it's finding boxes, different orientations, and you could run in behind it and change the configuration. It would notice it and then adapt to it. So it's that higher level of variance that we're handling. I'm moving on. This is the latest one. I might have to, the latest app. So we took that same software and we ported it. So this was a 4-week effort from complete scratch, from ordering the robot to bolting it up there to bringing in. But basically what it's doing is the same kind of thing as truck unloading, but in a different context, which is called depalletization. So, it's going and putting things in a beam breaker that measures the box and tells it where to drop off. And so this is something we did, well, it's actually ongoing, but this is 4 weeks from scratch, including building that end effector and putting the cabling on the robot, the whole thing. Anyhow, it goes on and on like this. One more. This is what I was working on last night, so I have to show it. Hopefully it'll start running. This is just barcode reading at fairly extreme angles. So, this is just showing the detection, but the detection is upper left. I just put it in one of the color planes, so it shows up as orange, but, and this is the green plane. I put the picture in, so the coloration is, but you can see there's extreme angles. It never misses and never gets a false positive. It can get fairly warped at some point, but the algorithm guarantees that a horizontal line will cross all bars, and that's the important thing for barcode reading. So that figure up at left that's the guarantee on it, that it tries to keep it rectified, but it won't do strange image distortions to do it. But it'll guarantee that one horizontal line will cross all the bars. And that's how we get, fast reading. This is for robots handling stuff, so I don't want them to have to spend time and wiggle the thing around. And so I'm putting the stress on the vision algorithm and not on the robot to do strange movements. Because everything we get, they want it to move, and so we can't afford slowdowns. So that's it. I don't know if there's time for questions.
Thanks a lot, Gary. I think we're running a little bit behind, but it's not really Gary's fault. We started a little bit late. We'll take one question now, and will you be able to stick around a little bit after your talk for more questions? Is there one quick question someone wants to ask now? Miran in the back.
Gary, when you normally do object recognition, you start off with a big database of samples and then use some machine learning algorithm to spend weeks and then learn a model for the object. But you show that from one sample, you could learn the model pretty fast. How was that done?
We're not in academics anymore. We use very simple models, very well engineered. It's a kind of sparse template technique, and the learning is really instantaneous. It's not, all the thought went into how the features and not the learning algorithm. It might do better under more powerful learning, but we're just working this by engineering. So everything has to be fast. We don't want probabilistic models because you'll get a phone call and it'll say it's not working in the field. You better know why it's not working. So it's very easy in our model to tell why it's not working. It's very deterministic. You could go right in and say, I understand why it doesn't recognize that view. And so that's what we want in it. And it's also extremely fast. I mean, it's fast in learning and fast in recognition. But we're not trying to learn 1,000 objects because we know basically what we're looking for, and we can just swap in whatever the few expected items. So really, it's more or less the nearest neighbor technique, but very cleverly aligned for SSE.
Yeah.
Okay. Oh, yeah.
Thank you very much, Gary. Excellent presentation.